You will now see and learn how I designed that light holder from scratch all the way to the end using one sketch in SolidWorks. You will understand the stages of my thoughts, the stages of my calculations, logic, modeling, and the tools I use in SolidWorks. Welcome back, I'm Aryan. If you're new here, I help engineers and creative minds to convert their ideas into real solutions through learning SolidWorks with a very easy approach. So don't forget to subscribe if this is something for you. Not in the exact previous video, but the video before it, I told you about the issue my friend raised about his lights and what I did to solve the issue. You can go watch that video first. Now I'm going to walk you through that solution and show you how I came up with that and how I optimized each component, made it perfect for manufacturing, and at the end I almost reduced the manufacturing price by 400%. Alright, let's define the issue thoroughly one time, then we will start with the solution. The issue. Here's the light. Rather a long stick with a small cross section, which makes it very unstable to stay on the desk, and the smallest vibration or movement to the desk will cause it to fall down, which during filming is a pain in the neck. Now, the solution. Well, it has some stages. Stage number 1, idea generating. First thing that comes to my mind is to design a piece of flat square with a hole on the bottom so I can screw it to the bottom of the light and it can increase the cross section on the bottom, therefore it will be stable. Sure, and it will definitely work. The issue with that is it's too simple and it cannot set any angles, and I wanted to have something a little bit more challenging. So while this is a good idea and it works, I cross it, which takes me to idea number 2. So to set any angles, I could work on something like a cannon that can change in angles, and then by rotating the whole base of it, I can basically reach any angle I want. But there are some further questions I have to ask if I want to go down this route. How do I fix that angle over there with a bolt and a nut? How tight should they be? Is it going to break the material? Whether or not it can hold the weight of the light, because the light is very unproportionate to its cross section. It's a very long piece of stick, and if one bolt and nut create an axis, it will not stay at that position. So while this might work, I cannot answer every question I have about it, so I would rather move on to the next idea. Number 3, a ball and joint, which can create any angle, and fixing it is rather easy using 2-1 screws. That's all you need. So all right, once I pick my favorite idea, I move to stage number 2, evaluating the challenges of that idea. All right, once I locked on that idea, I think ahead about possible design, assembly, manufacturing, and functional challenges of that idea very roughly. Here are the challenges. So let's, for example, let's go over some of the biggest challenges of this ball and joint idea. Number 1, it has a purpose and it has to hold the light. So I have to accommodate a fixture for the light to be to the holder, and I think a pocket would do nice. So if you have a pocket, we can insert the light in it. That should be fine. Good. Number 2, the tolerance and dimensioning of the ball and joint should be accurate, because if the joint is too big, the ball is loose that comes out. If it's too tight, you cannot even assemble them, and if it's too tight and you can assemble them, they would not move. So I have to take the tolerancing and the dimensioning of that, of those two components very seriously. All right, but doable, but I have to take that into account. Number 3, once the light is connected and the ball is placed in the joint, there should be a mechanism that allows the user to fix the ball in that certain position. All right, we said 1 or 2 screws would do the job, also doable. Next challenge. Number 4, once the light is connected to the ball and the ball is placed in the joint and is fixed in that position, now what? Now the light is very long. If it's tilted, is it going to stay there? Is the radius of the joint, which is the very base cross section of the whole assembly, enough to hold the light at that angle? All right, I have to take that into account too. And I think I'm happy with these 4 questions. And at this point, I would move on to the next stage, number 3, which is modeling. Let's start with the modeling. How do I start creating something like this when I have nothing? Everything starts with the final purpose, in my opinion, which is holding the light. So if this thing has to hold the light, it has to accommodate the pocket for it. Therefore, the dimension I can get and start working with is the circumference of the light. If I take that and somehow bring that into SolidWorks via measurement or any other method, then I can take it from there. I can create the inner sides of the pocket, create the walls of the pocket, and so on and so forth. So task number 1 is measuring the circumference of the light. And since in this case, it has a very odd geometry, nothing like a square or circle that I can use my calipers to measure, I would put it on a piece of paper, preferably gridded because it's already scaled, or a normal plane, and draw around its circumference as accurately as possible. Then if it's a plain piece of paper, I would draw a line next to it for 1 inch long as the reference. Because I have to scan this piece of paper, bring it onto computer, bring it onto SolidWorks, then scale it right. Because I cannot just import it into SolidWorks and start drawing on it. I know this line should be 1 inch long, so I draw a line, dimension it 1 inch, then try to scale the image as much as possible until these 2 lines, the one on the piece of paper and the one on SolidWorks, are exactly equal in length. Or if I use the gridded paper, I could use this grid as a frame of reference, 5 millimeters each, 7 of them, 35, and I can scale the image and take it from there. At this point, I'm confident that my sketch has been scaled into the right size, and I can draw on my sketch using 2D tools that the sketch toolbar of SolidWorks offers me. So 2 straight lines, and over here we have curves, and I'm gonna go with spline for these 2. We have 4 rounded corners. Different tools can take care of that. We're gonna go with sketch fillet and then round them. Okay? Now, once the sketch is closed, I have the inner sides of the pocket. Or do I? Because we have to talk about something very important, or else everything else we do from this point onward is gonna be a moot point.
It's moo.
The sketch is more or less as big as the light. We just drew it on a piece of paper and we scaled it right. But what if our manufacturing process's tolerance creates this pocket slightly smaller and our light won't fit into this pocket? If it happens, then it doesn't matter if the rest of the components line up and assemble together. The light, which is the final purpose of this design, wouldn't fit. Obviously, I don't know what 3D printer I'm going to use to print this, so I cannot take the exact tolerance into account. Some have bigger tolerances, some have smaller tolerances. Since this pocket doesn't have to be micro accurate, it's not a heart valve or anything like a rocket piece. It has to be rough, so I can go for a bigger size, making sure even the manufacturing tolerance makes it slightly smaller, the light can still fit into this pocket. For this reason, I offset this sketch for 0.2 millimeters or 7 thousandths of an inch from each side. That can be done using offset entities. I'm now done with the inner pocket, and the outer wall of the pocket needs to be defined. It's dependent on my manufacturing process again. Since I'm planning to 3D print this component, I think a 2 or 3 millimeter wall thickness would do fine. Since it's going to be from PA12, it's strong enough, it's not going to break. So I'm going to go with 3 and offset this value 3. That defines the outer edges of my pocket. Right, now we have one closed sketch. The length of extrusion, how much I extrude this sketch, defines how long I want my light to be inserted into this pocket. If it's too small, it probably tilt over. If it's too big, it's unnecessary. It makes the product more expensive to manufacture. I think a 50 millimeter long pocket, 5 centimeters, is good enough, and I'm gonna go with that. Right, it is symmetric, and all I have to do is close one of the openings, and that would be the pocket. Now we can take it from here. We have the pocket, The pocket has to be connected to the ball, but we need some sort of a neck between the pocket and the ball. So a neck can be something as simple as a cylinder. That would do the job. Or if you want to make it more robust or strong, we could use loft to take it from a rectangular cross-section all the way to a circular cross-section, which makes the modeling process a little bit more challenging, but at the very least you have a better looking and a stronger neck. Now, the height of the neck matters too. The longer it is, the more expensive it becomes and the more brittle it becomes. So you don't want to go too long, and going too short also limits your maneuverability. In this case, knowing this much is 35, I would go with 35 because it's not too long, not too short. It's not a golden ratio or golden number. You could go for that. The next feature we have to focus on is the ball, and it can be made using revolve. Of course, you know, you can draw half a circle, revolving it around its axis, create the ball. But what would be the diameter of the ball? If you go too big, first of all, it could create a stress point where the neck connects to the ball. Second of all, it creates more material, therefore you pay more for your 3D printing. And if you go too small, then again, it doesn't make sense and you have a hard limit. So it's again an experimental value. Based on my experience, I would go for like 30. That would still do 30 because the neck is 35. Diameter of the ball could be 30. I think it's a decent number. It could be more, it could be less. It's not pinpointed exactly where it should be, but that's what I went with. And now we are done with the moving part, okay? We have to take it from here and create the counterpart of this moving part, which will be the joint. And therefore, we are now at the next stage. Over here, we have to create the counterpart. My preference when it comes to modeling like this stuff from scratch is to work in the multi-body mode in SolidWorks. And if you don't know what multi-body mode is exactly, I have created a video, dedicated one video to that, and you could just go on the top right screen, to the top right corner of the screen, click on the info button, and then find that video. It is where you work with more than one solid body at a time, and I will explain what solid bodies are, and you can understand how to create more than one solid body in the part mode. We are not in the assembly mode. All right, where were we? All right, we were about to design our joint. So the first question that comes to my mind, what's the inner diameter of the joint? Or in another word, what would be the gap, the clearance gap between the ball and the joint, which is the pocket around the ball? Is 1 millimeter too much? Is 0.1 millimeter too small? Is it too tight to move? Then again, I don't know the manufacturing tolerance of the 3D printer I'm gonna be using. So unlike the previous pocket that were too rough, I could just make whatever I want, this one cannot be just too big because otherwise the ball would be too loose in the pocket. And I went with 0.9 millimeter. Again, based on experience from each side, I think that's a good amount because at the worst case scenario, the ball has less than 2 millimeters to move in each direction. If you know what 3D printer you're using and if you know what tolerance that your 3D printer has, then you should calculate the tolerance and use the accurate numbers. In my case, I had to take a smart guess. The inner size of the joint as well should be a sphere. So while I could just redraw another half a circle and revolve it around the ball, I would use a different technique, which is easier, by going to the surface tab, offset the surface from offset surface. I think it's a tool with a gap of 0.9 millimeter. And then I would create one surface body which has 0 thickness. So it's not a solid body. To turn it into a solid body, I use a thicken, which is another feature on the surface tab to give it some thickness. Doesn't matter how much, because we're gonna build on top of this. This is only the beginning of the joint. Right. Now, the joint, the gap is 0.9 and it's fine, but we have to go on to the next stage, stage number 5, and calculate the opening of the joint. Because yes, if you get your ball already installed inside the joint, even that design would work. although your maneuverability is much limited because of the opening you have here, but it doesn't come already assembled. You have to assemble them together. And if you make the hole too big, then the ball would not stay in the joint. It would just pop out. It's too loose. If you make the opening small, too small, you cannot even assemble them. So you have to find that perfect opening. Definitely not bigger than the diameter of the ball, because then it's already too late. It has to be smaller, but not too small. So how do I do that? Look, this is the cross section of the ball. Anything above this line, which is the diameter of the ball, is too tight. Anything below it is too big. Too big is definitely a no-go. We want to be in the too tight area, but not very too tight. We want to just be like in tight area. So why do I want to be there? Because I am printing this material from PA12, which is a resin, and it's not a metal. It's not aluminum or stainless steel. If it was, then definitely I would have wanted to be below this, or still I would be above this, but I'm counting on the flexibility of the material, so I could just maybe with some reasonable force press the ball into the joint and they would be assembled. So I want to be above this line, and I can calculate by drawing some lines what would be the opening, what would be the difference in size. My ball would be 30 in diameter, my joint would be a slightly smaller, and then I'm counting on some reasonable force again to press it with the hand into the joint. Now, once I do this, I have to proceed to stage number 6, which is designing the rest of the joint, because joint is not only carrying one function, it's carrying two functions. The first function is to accommodate the ball. Then the second feature is to have a big enough cross section so the light wouldn't tilt over. So we don't want to go too big because the 3D printing will become too expensive. We don't want to be too small, then we haven't solved any problem. The light will still tilt over. So you have to just work. If you want to calculate the exact numbers, you can. I'm not that kind of person. I cannot be bothered to go do those calculations. When it comes to these points, I have a good gut feeling about it, and I would rather rely on trial and error, because if it doesn't work in the first try for me, it will work in the second iteration. But it's a matter of iterating from this point, and the rest is garnishing. If you want to put a logo on it, just like the sketch in the beginning, you could insert your logo onto SolidWorks, draw on it, extrude it, and bring it onto your model, and then make everything look nicer. All right, before we end this, I said we need 2 screws to hold the ball tight. So I'm gonna make these holes onto the joint body, so when I get it from the 3D printing shop, I don't have to drill it. Although, as I said in the previous video, my mistake was that I only took 2 holes into account, and the holes lined up and they created some sort of an axis, which made fixing, or at least left the ball with 1 degree of freedom. We don't want to leave it with any degree of freedom. When it's fixed, it's supposed to be super fixed. So I had to drill a 3rd hole and insert the 3rd screw to make it super tight, which it worked. But I just wanted to walk you through my thought process, how I start from scratch and go all the way. Now, at this point, I have a component. I usually play around with it for sometimes hours. I look at it from different angles. I keep rounding any edge that I don't like, that I don't know if it's an OCD or anything, but once I get a good feeling about it, I ask for a quote. And this time I used Protic, which I've worked a lot in the past, and they are not sponsoring any of my videos, not at the moment. And yeah, I realized the price is too much. Every component was too big, and I knew, okay, it doesn't have to be too big. I don't have to design it so generous. I can make everything smaller, reduce the wall thicknesses, reduce the radius of the joint base, and all of that could help in reducing the price. So after doing this 3 times, I reduced the price from, I think from 500 to about 100 euros, which is about $130. And I think it was reasonable, even though it's too expensive for what it does. But for my purposes, which is kind of a research and development, it was good enough, and I ordered it and it worked perfectly. If you don't know how it looked, or if you haven't watched the previous video, I put the link again in the info card on the top right corner of the screen, so you can go there and watch it right now. All right, let's quickly go back to the other room so I can wrap this video up. All right, I hope you like this video. If you're serious about learning SolidWorks, I have put the drawing sheet of this component with the exact tolerancing and dimensions to download on my website. As usual, you can find the link in the description below this video. Also, while you're at it, I have 1 hour of training for SolidWorks, which covers the most common mistakes I see all SolidWorks beginners make, as well as their solutions, so you can fix them once and for all. Basically, if you are a SolidWorks beginner, or you want to make SolidWorks a part of your professional life for any reason, maybe you love creating stuff and you only miss the skills to convert your ideas into an actual model, then learning SolidWorks is going to be the solution. Is going to solve that for you once and for all, and I'm here to help. Check that training, which currently is on my website, and at the end of that, I will grant you an access to my mini course. The download sheet, the 1 hour training, as well as the mini course are free, by the way. You don't have to pay anything. So click on the link below or on the top right corner in that info card. Go to the website, register, get your download sheet, get your mini course, and watch your training. And I will be back this week again. So if you like what you saw, hit the like button and don't forget to share it with your friend so they also like this video. I'll see you soon.